And yeah, so we are MLBs because, of course, we had to choose a silly acronym, and it's short for Machine Learning-Based Emulation of Land Surface Models. In this case, that's EasyLand. So why you might be interested in these talks could be the following reasons. So, I mean, we already heard that machine learning is all the rage now. You trade off a bit of accuracy, but what you get is a lot of speed up, so that makes it interesting for a bunch of applications. And in this case, it is no different. My personal highlight, though, is that we tried a variety of architectures. Sometimes that's not all too exciting because you should see then a model comparison where you see some small changes in some model metrics, which can be quite abstract. But what we really saw were some appreciable differences in qualitative differences in the model outputs, which you can then also try and explain either by physical reasoning or by the model architecture itself. And since we tried a bunch of architectures, we had to come up with a simple automated evaluation script. This should be easy to add on to later if that's desired. But we also wanted to make sure to do an in-depth evaluation because with these statistical models, there's always an issue with how reliable are these outputs really, and that's why we tried to scrutinize them. And then we'll start on a visual highlight. So Johannes prepared this nice animation. On the left, you can see EasyLand, so that's the original. On the right, you can see one of the emulators, and this is layer 1 soil temperature for a year. Just for you to see how similar or different it looks, and what kind of data we're talking about. Before we get into the details, though, I want to take a little step back because maybe not everyone's familiar with land surface models. So what they do is they solve the energy, water, and carbon fluxes at the land surface, and then you use those to predict future time steps, so soil moisture, soil temperature in this case. You could either use the standalone for flood or drought forecasting, or you could use this, mostly use this in a coupled fashion with a weather prediction model because, of course, the exchange between land and atmosphere is quite important for getting the weather right. And here on the right, you can see a schematic of EasyLand. So this is not for you to read through, of course, but just to appreciate that there's a lot of processes going on. And so it takes a bit of computational effort to actually solve all these equations that come into play here. And what Ewan, who just introduced us, nicely demonstrated with this prototype already is how much of a speed up you can get. So if you run this full model for a month at a global 30-kilometer resolution, this will take you like 20 minutes approximately. And if you go to machine learning, then you can really go down to a matter of seconds. So that's quite impressive, I think. So what we did in our projects were mainly two pillars. So on one side, we have the model development part. There we wanted to improve on AR-Land by unifying the data processing pipeline, testing different methods, as I already said, incorporate some observations, and then also we wanted to try and constrain the emulator to be physically consistent in the outputs where possible. And this goes hand in hand then with the evaluation part. So we had to look at accuracy and at the speed of these different versions. And then in the in-depth evaluation, we looked at spatial and temporal error variability. So what we mean by this is we had the feeling before we started that maybe there might be some regions of the Earth which perform better or worse. Maybe there are differences between seasons as well, and this is what we wanted to find out. Then when we incorporate observations, we also want to compare to observations as well, test the physical consistency, and have a look at uncertainty as well. And now Johannes will start by talking a bit more about the model development part.
Yes, thanks to. Next up, I will give a bit of an overview about which kind of methodologies we actually used to emulate this EasyLand model, and also just how it all works. So starting out with more or less the inputs to the model, we have, of course, most importantly, some model states, which here, symbolically, you can imagine just one model state at some time point. So this contains information about like soil moisture, temperature at various layers within the soil, and also the snow cover. And then, of course, we also have some auxiliary information, and this can be static conditions, like information on the topology or the land cover. But it can also be dynamic, so this includes the weather or vegetation-related variables like the leaf area index. And then what we also add is additional inputs. Is spatial and temporal encodings, and these basically inform the model about where on Earth a certain data point is located, and also about the time within the year, or also the time within the day that we actually try to emulate. So all of this is fed into AI Land, which for now, for the time being, could be any machine learning model actually. And this machine learning model is then trained to predict, on the one hand, some state increments. So basically how soil moisture, soil temperature, and so on progress from one time step to the next. And it also predicts some diagnostic variables, which are basically variables which are not directly incorporated in the model state, but are still interesting in terms of land surface modeling. And then, of course, we can use this emulator as we do the regular model iteratively. So we can use the predicted state increments to update the state and just rerun the model. Okay, so next I will talk a bit about data preparation, which I know is for a machine learning audience always a more or not so interesting part, but it actually was pretty crucial for us to take good care of this. So first of all, we have like the EasyLand output for a grid over Europe. So this is a model run which is at a 6-hour interval from 2010 to 2022, which we divide into like training, validation, and test set. And then we have to take some care about the standards, data standardization, because of course all these variables which I mentioned don't share units, so we standardize them by mean and standard deviation. And also for the increments, we found it important to standardize not on the original variables, mean and standard deviations, but actually those of the first differences to actually get a stable model run going. Okay, so this data is now trained to used to train a machine learning model, and here we actually compare 4 different ones, which you can see on the left. So first up we have XGBoost, which is basically an ensemble, a boosting ensemble of decision trees, regression decision trees. We train up to 1,000 of these until up to which it's still sort of reasonable to go up in size. And these decision trees, they basically use a gradient boosting mechanism to iteratively minimize this some predefined loss, in our case the mean squared error loss. Then we also train a multi-layer perceptron, which is a very simple neural network. We use dropout and also train it on the mean squared error loss. So both of these models, the XGBoost model and the MLP, they basically run grid cell-wise, so they can only predict the predictive variables at a certain time step at a certain location. And to improve upon the situation, or to also look at other possibilities, we have the other 2 neural network architectures. The first is a graph neural network. So graph neural networks, as their name suggests, operate on graphs rather than individual data entities. So this basically enables us to also incorporate some spatial information into the network architecture. So throughout the network architecture, neighboring grid cells are able to communicate, and we were hoping that this would basically improve the network capabilities. And then secondly, we also want to take into account temporal information by using this Mamba architecture, which basically operates on sequences. So instead of just taking a previous time point, we can actually train the model on sequences of up until, I think, 64 data points rather than just the previous one. And also a note, so this relies on, this model basically relies on selective state spaces, which is a bit more efficient than the transformer architectures that you may know. Okay, so now for the actual evaluation of all these models and the comparison, I will hand over to Yikui.
Yes. So thanks for Johannes for introducing the methodology and machine learning model. So to evaluate our machine learning emulators, so we first streamlined the automatic evaluation framework or workflow to calculate the evaluation error matrix from using data from both the EasyLand model and also the validation data set to evaluate our AI land model, our machine learning emulators. And at the same time, this automatic workflow is also used to visualize the spatial error map of the evaluation result, and also finally to automatically generate a scoreboard to summarizing all the results. And based on this evaluation matrix, so we further did statistical attributes, conditional analysis, and also uncertainty analysis, as well as the physical consistency analysis. So first of all, we summarized the result of our 4 AI land model or machine learning emulators in the result for all the target variables, or 16 target variables into this scoreboard. So here we only show the example of the anomaly correlation coefficient as the evaluation matrix. So basically this matrix, it means if you can easily understand it's close to 1, the better the model performance. So here we can easily see that actually the XGBoost model performs best for most of the variables. And it's very interesting to see that the XGBoost model outperforms most of the neural networks. And among the 3 types of neural networks, we can see that the Unimap model, the graph neural network model, outperforms other types of neural networks. And despite of the difference between the model performance among these 4 types of machine learning emulators, actually all of them can achieve a very good performance for most of the variables. And the only exception is for the discharge and also the surface runoff. And we can see that here for all these machine learning emulators, the anomaly correlation coefficient is lower than 0.5, which we can say that there is a very low emulation performance for all these 4 models. And on the other side, so considering the trade-off between both the accuracy and the efficiency of the machine learning emulators, we can say that the MLP model actually is the most efficient model we have, because it can achieve for its inference, it can achieve 44 time step per second in the inference, and this is around 7 times or 6 times faster than the XGBoost model. But of course, this is somehow sacrificed its emulation performance. Next, we visualized. We want to show the spatial error variability of the machine learning emulator. So first, here we show the example of the anomaly correlation coefficient of the layer 1 soil moisture for the 4 types of machine learning emulators. From these 4 figures, we can easily observe that actually our machine learning emulators can achieve a really good performance in most of the regions in Europe in our target domain. We can see that in most of the grid points, the ACC score actually is very close to 1, which means that the emulation performance is quite good. And however, there's also one interesting pattern, is that all the machine learning emulators somehow struggle in the Scandinavian regions. And especially for the MLP model, is this low performance somehow extended to the east part of Russia. And this is likely attributed to 2 reasons. So first is the difficulties for the machine learning models in emulating the snow melting processes in these cold regions. And the second reason could be related to the difficulties of the machine learning emulators in dealing with some special land cover type, for example, like lake or glaciers. And next, we also did some analysis to test the physical consistency of our machine learning emulator. So here we show an example of the sensitivity of the soil moisture to the field capacity. So in this figure, we show the sensitivity of the soil moisture to field capacity calculated by the MLP model, and we can show, and these points basically represents the relationship at different selected locations in Europe. So here the MLP model shows the gradual reaction to the changed field capacities. However, sorry, we didn't show the figure here, but the same figure for the XGBoost model, it shows that average soil moisture jumps at the learned field capacity threshold, and this is corresponding to the different soil types. So this is somehow related to that tree-based model is it prefers or it tends to learn a discrete relationship rather than a gradual change. So last but not least, we also try to evaluate the uncertainty associated with our machine learning model. So in this project, we only focus on the epistematic uncertainty, and in order to capture this uncertainty, we adopt a method called deep ensemble by simply creating an ensemble with 30 UniMap model members with exactly the same neural network structure, but slightly different initial condition, or basically the slightly varied parameter size for these 30 neural networks. So in order to quantify the uncertainty, we calculate the continuous ranked probability score for the spells at both spatial and temporal scale. And this, you can easily understand this matrix is close to 0, the better the performance, or the lower the error of this ensemble. So from this figure, we can show the spatial variability of the CRPS score, and we can actually see that it shows a very similar pattern to what we have observed in the previous spatial error variability analysis. And we can see most of the places there is a very low score, which means that the uncertainty associated with the ensemble is quite small, but there is a relative higher score in the Nordic region, in Scandinavia regions. And actually, this further demonstrates that our deep ensemble method can somehow provide a very reasonable estimation of the uncertainty, because the well-calibrated machine learning model should provide small uncertainty in regions where we have a small model error, and high uncertainty in regions where we have high model error. And finally, I will hand over back to Theo for the conclusion.
Yeah, thanks. Yeah, there would have been a lot more to talk about, but there's no reason to be sad because everything's on GitHub as well as the documentation. So just a few take-home messages. So we saw that XGBoost is already sufficient for emulating ECLAN, which was quite a bit of a surprise to us. There are a few drawbacks, so it's a bit slower and it's a bit less flexible than other models. And also we didn't really show that here because of time, but we saw how including these spatial relationships really helped in mitigating some of the artifacts. So if you predict every grid cell by itself, of course, it can then lead to some discontinuities in the spatial domain. We saw how, exemplified by Scandinavia here in this one map, the emulators all struggle a bit with cold regions, especially glaciers, and also waterlogging areas, so close to lakes, marshes, also are a bit of a problem. The good news in terms of the temporal error variability, so it's boring, that's why we didn't show it, is that the seasonal and the diurnal cycle work quite well, so there's not much difference in performance between autumn and winter, for example, or between day and night. And so finally, I would like to use this opportunity to thank all of our mentors. We had really great discussions and learned a lot, so we really enjoyed that. And so if you have any questions, feel free to ask them. Thank you for listening.